Welcome to this lesson on hypothesis testing. Imagine you are a bouncer at an exclusive club, tasked with keeping out anyone under 18. You could draw a strict line on the wall and reject anyone shorter. Or you could check their ID and calculate the exact probability of their age. In statistics, these two methods are known as the classical and p-value approaches. Today, we will explore how both methods help us decide whether to reject a default assumption, known as the null hypothesis, and why they always lead to the exact same conclusion. Now that we understand the basic goal, let us look at how these two approaches function. In statistics, our main objective is to decide whether to reject a default assumption, which we call the null hypothesis. The classical approach is like drawing that strict line on the wall. It sets an unmoving boundary, and anything past it is rejected. On the other hand, the p-value approach is like checking the ID. It calculates the exact percentage chance of observing your data if the default assumption were true. Even though they use different mechanics, both methods will always lead you to the exact same final decision. Let us dive deeper into the first method. The classical approach, also known as the critical value method, is the traditional way to make decisions. You start by choosing a level of significance, denoted by the Greek letter alpha. This alpha represents the maximum risk you are willing to take of making a false alarm, meaning rejecting a true default assumption. Based on this risk, you find a critical value, which acts as a strict border, dividing all possible outcomes into a safe zone and a rejection zone, formally called the critical region. You then calculate a test statistic from your data to see where it lands. This brings us to the mathematical rule for the classical approach. Conceptually, you are setting a trap with a fixed boundary, and if your data steps into that trap, you throw out the null hypothesis. The formula is z-calc greater than or equal to z-alpha. Here, z-calc is the test statistic calculated from your sample data. Z-alpha is the critical value determined by your chosen risk level, alpha. If your calculated value is greater than or equal to the critical value, your data has fallen into the critical region. As alpha decreases, meaning you want to be safer from false alarms, the critical value moves further away, making it harder to reject the null hypothesis. Now let us look at the modern alternative. The p-value method is heavily used by computers and statistical software today. Instead of setting a fixed boundary beforehand, this method calculates a specific probability based on the data you actually observed. The p-value is defined as the probability of getting a test statistic at least as extreme as yours, assuming the null hypothesis is completely true. Think of the p-value as a measure of surprise. A very small p-value means your data would be incredibly rare and surprising if the default assumption were true, leading you to conclude that the assumption must actually be false. This concept gives us the golden rule of modern statistics. To make a decision, you simply compare your calculated p-value directly to your chosen risk level, alpha. The formula is p less than or equal to alpha. Here, p stands for the p-value, which is a probability ranging from 0 to 1. The symbol alpha is your level of significance, typically set at 0.05, which is a 5% risk level. If the chance of seeing this data by pure luck is smaller than your allowed error limit, you reject the null hypothesis. As the p-value gets smaller, the evidence against the null hypothesis gets stronger. Before we move on to examples, it is crucial to understand how these two methods connect. The classical approach and the p-value approach are mathematically equivalent and will always yield the exact same final decision. The classical method compares distances on the horizontal axis of a graph, checking if the test statistic is pushed further out than the critical value. The p-value method compares areas under the curve of that same graph, checking if the tail area beyond the test statistic is smaller than the tail area defined by alpha. They are simply two different languages expressing the exact same truth. This diagram perfectly visualizes why both methods agree. Look at the horizontal axis. The light red area represents our strict risk limit, alpha, and its starting border is the critical value, Z alpha. Our actual data, zcalc, landed further to the right. Because it crossed that border, it created a much smaller dark red area, which is the p-value. You can clearly see that because the data crossed the distance boundary, the dark red area is guaranteed to be smaller than the light red area. This is why both methods always lead to the same conclusion. Let us see this with a concrete example. A company claims their batteries last exactly 50 hours, but a consumer group believes they last longer. They test a sample and calculate a test statistic of 2.15. The chosen level of significance is 0.05. From statistical tables, the critical value for this right tail test is 1.645. Using the classical method, we compare the calculated value directly to the critical value. Since 2.15 is strictly greater than 1.645, it has crossed the boundary into the rejection zone. Now let us solve the exact same problem using the p-value method. We must calculate the probability of observing a test statistic of 2.15 or even larger, assuming the company's claim is true. Using a standard normal table, we find the area to the right of 2.15 is 0.0158. This means there is only a 1.58% chance of seeing this data by luck. We compare this p-value to our significance level of 0.05. Since it is strictly less, the result is highly surprising. We reject the company's claim, perfectly matching the classical conclusion. Let us look at a second example, this time a two-tailed test. A factory machine should fill bottles with exactly 500 milliliters. The manager tests for overfilling or underfilling using a significance level of 0.05. The sample yields a test statistic of negative 1.90. Because it is a two-tailed test, the risk level is split, giving critical boundaries of negative 1.96 and positive 1.96. We compare our test statistic to these boundaries. Since negative 1.90 falls safely in the middle non-rejection zone, under the classical approach, we fail to reject the null hypothesis. Now we apply the p-value method to the same machine calibration test. For a two-tailed test, the p-value is the probability of being that extreme in either direction. So we find the area to the left of negative 1.90, which is 0.0287, and multiply it by 2 to account for both tails. This gives a final p-value of 0.0574. We compare this to our significance level of 0.05. Because it is greater, the probability is not low enough to be a statistically significant anomaly. We fail to reject the null hypothesis, meaning the machine does not need recalibration. You might wonder why we need both methods if they always give the same answer. The classical approach was invented first, back when statisticians had to rely on printed paper tables. It is much easier to look up one critical value boundary and compare your number to it manually. However, the p-value approach is the standard in modern science, medicine, and business because computers can instantly calculate exact probabilities. A p-value gives you much more information than a simple yes or no. It tells you exactly how strong your evidence is, which is essential for scientific discoveries. To wrap up our lesson, let us review the key takeaways. The classical and p-value approaches are two sides of the exact same coin, used in hypothesis testing. The classical method sets a fixed boundary on the graph and checks if the test statistic crosses it. The p-value method calculates the exact probability of the observed data and checks if it is smaller than the allowed error rate. While both methods will always agree on whether to reject the null hypothesis, the p-value provides a deeper, more precise understanding of the strength of your evidence. You now have a solid foundation in both approaches.